Season 3, Episode 1. First, you need light. And welcome back. Welcome back to another edition of the s3e1 podcast. Emily, I know I've said this in the past, but I'm going to say it again. It's been a while. Yeah. But we are back. We are back for officially season 3.
Yes,
this
right.
is season 3, isn't it?
3.
We had a really long season 1.
Like 200 episodes.
Not quite, but close to 120. And then we had 6 episodes of season 2.
Yeah.
And we had a long break because it's been a big year. It's been a lot going on.
You've got new glasses.
I have got new glasses.
Yeah.
Yeah, or indeed glasses. The newness of that. Yes, listeners, I'm getting older and I can no longer see. So I now have an interesting pair of glasses. That's how long it's been. I've gotten old enough to need glasses. Yeah. So late 2025. Here we are, season 3.
We are.
Now, last season, remind us what last season was all about.
Well, it was insert another object from the astrophysical universe here.
Yeah, so we had exoplanets, obviously. We had exomoons. We had exocomets. Whole bunch of exostars.
Exotelescopes.
Yeah, and then we ended with, if I'm right, sort of tantalizing hint for months down the line, and here we are. We're talking about exolife, as in life in other solar systems, around other stars and so on. And then we thought, why don't we just do an entire thing on that? Let's do an entire series. So this series is going to be about life in the universe, life amongst the stars, Emily.
Yes.
Where are we going to go over the next 6 episodes? Just broadly, what are we going to touch on?
Well, we're going to start, of course, with the light itself. We need to know where our light is going to come from for our life. We're then going to have a look at some of the interesting places we might be looking for life. So where is it actually, what sort of habitability, what sort of environments might be interesting to look at?
If you were going to look for life in the universe, under what rocks would you look?
Well, indeed.
Yeah.
The green ones, obviously.
Yes, clearly.
Yeah. With the slime on top.
Yes, that's the way that works.
Yeah. We're then going to start to look at, actually pull back a little bit from that point and look at the solar system and actually, hey, we can learn a lot about solar system environments, whether or not there may be life in those. A little bit about, hey, what is life? Because maybe we should address that at some point.
Yeah. I mean, we're not going to start with that. That would be the obvious place to start. But no. Far be it from us to start with the obvious one. No, we'll put that one off for a couple of episodes, but return to that thorny question of what are we even talking about?
Mm-hmm. And then the signals that this questionable life may or may not produce that we can therefore find out about.
Yeah, because it turns out we can't actually go and just always lift up a rock. You know, we might be able to do that a little bit on Mars at the moment, but otherwise we're kind of limited to seeing signals from somewhere else. And so what sort of things are they?
And then to wrap up, so actually what are our hopes, our chances?
Because
is this actually really going to happen?
Yeah, we're still at an N of 0 currently on life outside of this planet. So, what are the odds? What are the chances that we're going to actually find anything? Anywhere from 0 to something. Cool. So that's where we're going, right?
Yeah.
Over the next 6 episodes. But today, we're going to start at the very, very beginning. In the beginning, there was the light. Mm-hmm. Emily, what are we talking about today?
Well, you've got to start with light. First, you do need some light. And
why?
Where does that light come from?
Why are we starting with light?
Why would you not start? First of all, why would I start with light?
Well, okay. Let's just be like all the cards on the table.
Yeah.
You are a stellar astronomer.
Yeah.
And I'm not just saying that you're really good. I mean, you are an astronomer who studies stars.
Yes.
Right?
Yes.
So, sure, you would say that. But why in this topic, the topic of life in the universe, why are we staying with light?
Well, the relationship really between light and life seems to be, first of all, fairly obvious when you look around us at life on Earth. But it doesn't take very long to start digging into that to say, okay, you might be able to come up with some wonderful examples of life on Earth that doesn't use light.
As an energy source.
As an energy source.
Yeah.
There's some, right? But the whole planet and the fact that we have life on our planet and therefore we have species of life that don't need light actually all come back to the fact that we do have light. We have a sun, we have a star, and stars are fundamental.
Yeah. I mean, it's one of those real amazing moments of studying science at school is when you first encounter that concept of like all the energy that we use and all other animals, asterisk, on Earth, and the asterisk is maybe there's something down by a geothermal vent somewhere that gets its energy from somewhere else. But everything else and all other sources of energy, asterisk, except for, radioactive elements. And even then, if you want to talk about supernova, anyway, it's all coming from the sun.
Yeah.
It's all coming from a star because, the light makes the plants and we eat them and so on. So that's one of those amazing moments where you suddenly realize, no, we really, we need that thing. It's not just for the light and the warmth.
No, we need it for the energy. We need it for the climate. I mean, we've seen examples of climate gone wrong in our solar system. So Venus, greenhouse effect, too hot, not so fun.
Not a great place.
Mars, not enough atmosphere, not enough warmth, very cold, also not so fun. Mm-hmm. We also need it for things like chemistry, for what we call photochemistry. So the sun's rays of light will come, particularly those in ultraviolet, break up some of the molecules in the atmosphere. That's needed again for further biochemical processes. So there's lots there. But if you really want to go super basic...
Yeah, okay, let's start at the very beginning. Go on.
We're not going to have a planet without the formation of a star.
Fair point. Okay, all right. If you haven't got a planet, you haven't really got much of anything to stand on, to be honest. Yeah.
And all planets, as far as we understand, are formed as a byproduct of the formation of a star.
Okay. There aren't planets that are just forming out there independently in the void going, I think I'll be a planet now. It's all part of a stellar, disk.
Yeah.
Collapsing down, forming stuff.
Exactly. So you need a star to form your planets. And we don't have any evidence that any planet should be otherwise.
Okay, so let's take that as our baseline.
Yeah.
If we're looking for life, there's going to be a planet involved. And if there's a planet involved, then there's going to be a star involved.
Yeah.
Okay, so that's number one.
Yeah.
All right, where do we go from there?
Well, maybe you need to look at kind of what is a star.
Okay.
Because the planet star...
Have we not answered that in 120, 130 episodes?
I feel like we've skipped around the edges a little bit.
If we haven't, we've really missed a trick. Okay, Emily, what's a star?
What's a star?
Let's go with that.
Well, if you want to start with the right words to use, we really want to start with plasma.
Okay.
So we're talking about a ball of plasma that is formed into a shape, a sphere, under its own self-gravity. That is sufficient mass that it means that the plasma or the core of this sort of ball of what maybe originally was gas and is now compressed plasma, the center of it is now hot enough to sustain hydrogen fusion into helium. So you need to have that fusion process to be a true, at least standard operating procedure star.
Okay. All right. So you need, at least for and I'm sure, because we've talked about this enough, Emily, I know that there are probably all sorts of asterisks and footnotes and, it's not as simple as that around this definition. But our working definition, big ball of gas/plasma, condenses under its own gravity, gets hot enough and dense enough in the core that fusion reactions turn on and become self-sustaining over time.
Yep.
That's a star.
That is
good.
A star.
Fantastic. Easy. Move on.
Yeah. So now the thing with stars and planets, therefore, is that the relationship between stars and planets is, for the vast majority of systems, totally entangled. You cannot think about one necessarily, certainly not the planets, without the stars. They just influence all aspects of how they are formed, how they evolve, because stars are always going to be the dominant gravitational mass in the system. They're going to be the energy producing source in the system through that fusion. So they're always just going to be the big guns, right?
Yeah. They are the dominant factor.
They are.
Yeah.
And we have talked about in the past about how we've got things like rogue planets that are off without a star of their own. We're just going to park those for now. They formed with a star. They're out there on their own now. We're not really, let's be honest, considering those as the best places to find life.
Yeah. I mean, I think if you did find life, it'd be just clinging on.
Yeah.
Just clinging on by a thread.
Don't say that too quickly.
Exactly. Through the void. Yep. So let's ignore that.
Yeah. So, and that's not true for the vast majority of planets that we've detected and understand. So most of them very, very intricately linked with their host star. And so therefore, to know your planet, you've got to know stuff about your star. And there are some really basic parameters that we start off when we say, let's look at a system, planet, star. Let's look at what the star's like. What do we want to know about the star?
All right. So where do we begin?
So we might begin with something like temperature of the star. This is pretty obvious. If you have a hot star or a cool star, that might influence how hot or cold your planet is, right?
Now, in terms of like on this scale of hot to cool, it's all pretty hot. So where does sort of hot begin? Like we have a star and it's big yellow ball in the sky and it feels pretty hot at this distance. Is the sun a hot star? Is it like, where does it sit in the scale of things?
The lower middle
Yeah.
section of the range. So with temperature, what we're talking about really is surface temperature. So this is the surface that we see the photons, the light, come from. We measure what the temperature is of that.
Right. The bit that we would see is that's the star.
Yep.
That's the sun.
Yep.
That's the bit we can
it's
see.
the yellow bit.
Yeah.
Right.
Yeah.
So that range goes from kind of about 2,500 Kelvin at the coolest stars. They look very red, up to tens of thousands of Kelvin for the hottest stars, which are very blue. So it's quite a big range.
That's quite a lot. That's order of magnitude. That's a lot.
And for the most part, there are certain properties of stars that match that distribution. So what I mean is that if we talk about the stars in the same point of their life cycle, which by the vast majority is going to be what we call the main sequence, middle age, where a star is doing exactly this, fusing hydrogen to helium. Stars do nice things before they're born and become a main sequence star. They also do very interesting things afterwards as they become whatever they're going to become after they've done all this hydrogen fusion. We're going to ignore both of those.
Okay.
We're just going to go with
just going to stick to we know what we're doing. The star's in a groove. It's got its thing happening, and it's just happy kicking along, saying, "I'm a star.
Yeah.
I'm not going to do anything fancy. I'm not going to try any tricks. I'm just being a star."
And this is by far the longest part of any star's life cycle anyway, so it's the most important, right? Now, if you talk about all the stars that are all merrily out there doing this hydrogen fusion on the main sequence, their temperatures can range, as we say, but there's also other things that sort of match that temperature. We actually mentioned already color. Color and temperature are kind of interchangeable on that scale. But we also have mass and radius. So it turns out that those cooler stars on the main sequence are actually also less massive, and they have smaller radii, or are physically smaller.
And I'm guessing that's because the thing that turns on the nuclear reactions, lots of mass squeezing down under its gravitational attraction. And that squeezing down increases the pressure, increases the temperature. The more stuff you've got, the greater that squeezing down is, the hotter you get. So if you don't have as much stuff, it just doesn't get as hot.
Yeah, that's a pretty good analogy. Yeah, and it's how, and also the size is dependent on the surface temperature, because if you've got lots of energy being produced in the core of your star, it's got more pressure, radiation pressure, to push out, become a bigger star, have a hotter surface. Right?
Okay. All right. So we've got temperature, mass, size.
Yep. So they all basically track on the same sort of scale, right? So you have this nice relationship: small, hot, dim stars, big, bright blue stars, very hot. So this is kind of nice. You can sort of navigate your way around the range of stars from there.
But the point is, all of these can end up on what you called the main sequence, and they're all quite happy, at least for a while, just being stars. It's not that the cool ones do anything ridiculous or the hot ones do anything particularly ridiculous. They're all fitting our definition of these are stars.
Yeah.
Yep.
Exactly.
Good.
And now, so if you go out and sort of look for planets around stars, you might find some around hot stars, you might find some around cool stars, and that's fine. But you can sort of get some general idea of what the star is like from those. Then you've got to start introducing another dimension to your thought process at this point, and that is time. And time is really important, and it's probably the easiest thing to forget when we talk about planets and how they habit or not. But stars have lifetimes, and in what you might think would be a reversal of how you would go through the logic, the hottest stars, even though they've got the most fuel inside of them, they burn through their fuel the fastest, and so they actually have the shortest lives.
So even though they've got more, stuff, because they're burning through it faster, they last the shortest.
Yeah.
Right, okay.
So big hot stars have very short lifetimes. And conversely, the very small red dim stars have very, very long lifetimes. This is important because, and we're going to come back to some of these ideas, but old stars have issues with how their planets might look and some of the parameters that planets might have. And young stars, well, they might just not be around long enough to even have a stable planet and a stable life, therefore evolve on that planet.
Sure. So when we're thinking about it in terms of, the characteristics of the stars and the characteristics of their planets help us to think about, all right, how do we go about thinking about whether or not there might be life on those planets? We've then got to start thinking about, all right, well, how long have they been around? How long have they had to evolve? How long, just as a system, let alone before you start thinking about life evolving, how long has this system been around to actually be able to do anything as interesting as the possibility of life? So how can we start thinking about that?
Well, it's tricky, isn't it? Because you've got to take in 2 time points really into your thoughts. You've got to think about how long is a star going to live for its entire existence. Those very hot, bright stars are only going to last for a couple of million years. It's just not long enough, right?
Only a couple of million.
Yeah, the very hottest ones.
Which is nothing on the scale. Like, again, if you think about life on Earth, it's billions of years.
Well, it's 60-something million years ago since we had dinosaurs, right?
Yeah. So, it's long time frames.
Yeah.
So you haven't got enough time for dinosaurs in a star which is only, a couple of million years before it puffs itself out. Yeah.
Whereas those dim red stars that aren't very massive, they can live for tens of billions of years.
Right.
Some are basically nearly as old as the universe.
Yeah.
So you've got lots of time with those ones. But then you've got to think of, we only live right now. We're not able to...
Yeah, we don't have the ability to do this experiment lots of different times.
No.
We're looking at what we've got now.
We're looking at a snapshot.
Yeah.
So even if you took one of your very small, dim red stars, if it's only been born a few million years ago, it might actually not be very helpful.
Yeah. There's a theoretical question around, would a small, dim, cooler star have a higher chance or not of having life over its lifetime? But we can only look at what we've got now. We can only look at what we can see now. We can't really find out whether or not billions of years in the future star X might have life.
Yeah.
And just as an anchor point, like, our sun is how old at this point?
So, well, we're talking about maybe 10 billion years.
Right.
Well, it's going to last for 10 billion years, but then we're about halfway through that.
Yeah, because Earth is about, 4.5?
Yeah, so the sun is about 5.
Yeah. And we think the earliest life on Earth actually came reasonably quickly.
Yeah, I think much quicker than... It didn't hang around.
No.
It got onto the job of
which is
becoming
interesting
life
in itself, and we'll probably come back to that in later episodes. But life on Earth is several billion years old, right, from its absolute most basic forms. So that just sort of gives us a little bit of an anchor on, the N of 1 that we have, life formed around a sort of middling yellow star, couple of billion years into its lifetime, and didn't take terribly long to kick off. But if that's anything representative, you need a bit of time.
Yeah. So you just don't want the super young systems, whether or not they're big or small, basically.
Sure. Okay.
So that's kind of your basic. Let's just lay out what category of star have you got? And astronomers are actually very good at classifying things. We like to put stars into boxes and say, here's all the stars that look like this. We're going to call these A stars. Here's all the stars that look like this. We're going to call them G stars.
I'm going to go out on a limb here and say that not all of your nomenclature makes sense.
Oh, none of it does.
But at least you're pretty good at making boxes. Okay.
Yeah. So we've got a wonderful sequence that goes from hot to cold. If you really want to go into the nonsensical list of letters, it goes O, B, A, F, G, K, M.
Okay, I can't help myself. Why that order?
Well, I think it's a bit historic. So when in the early days of spectroscopy, so looking at the chemical fingerprint of stars, there was stars, we didn't really understand exactly what we were looking at in the spectra. So it was just like all the stars that look like this one, we're going to put in this box and we're going to call this one A.
Right.
All the stars that look like this one, we're going to put in this box and we're going to call them B.
That makes sense.
And
I'm
then
liking
C
this.
and
This is a system. This is an organized system. What happened?
Well, we learnt some science
Right.
and we found out that there is a temperature sequence here.
Right.
Some of the boxes were merged. Some of the boxes didn't need to exist anymore. Some new boxes had to come along a lot later.
Right. So someone had to come in and go, all right. We're going to need to reorganize this. We're going to put O over here, and then was
B.
it O, and then B, and then
F,
and then, okay, and it messes all around. Because we're not just going from here are a bunch of things in a box.
Yep.
It's now the order of these is based on temperature.
Yes.
Okay,
So that is why we got our silly
sure. No, I can see
jumbled
that.
up list.
That makes sense.
But, things are, I mean, you could suggest renaming them from A to whatever. But I think that would be unpopular.
Yes.
Yeah. Anyway, so that's the very basic kind of ground zero of understanding a particular star. And then you can compare it to all the other stars that you know that are similar to that, and it will behave largely the same. However, there are some further complicating factors with stars.
There are.
Actually, it turns out that two stars of exactly the same mass, radius, temperature can have other things that are different.
Like what?
Well, I wrote down off the top of my head 4 things that can be quite different. And they're sort of semi-linked, well, some of them are linked. But anyway, so we can start with those and
All right.
see how we go. So the first thing that's quite interesting that can be different between stars of otherwise very similar parameters is the activity levels of a star. And I wrote this down first, actually, because it's very, very important if you want to think about life.
Okay.
You kind of want, in general, a star that's kind of active, but not too much.
So when you say active, just paint a picture for us here. What do you mean by
So
active?
it's not got its weights out and doing a 5K
It's
at
not
the
leaping
moment.
about the place.
No.
But what is it?
So we're talking about activity that is linked to magnetic fields, which we'll come back to. So this is spots, star spots, flares. In terms of our own sun, we see things called coronal mass ejections, which are just basically flares that are massive, really, really
right.
big.
And ejecting. So basically what we're saying is bits of star coming off at high energy and speed into space.
Yes.
And hopefully not in our direction, because that would be bad.
No.
Yeah.
Exactly.
Yeah.
So,
but this is stuff that we're familiar with from our sun. Like
Yes.
our sun is active.
It is.
and sometimes more, sometimes less.
Yeah.
Right.
So our sun goes through cycles of activity, but on the whole, if you took the average, our sun is a fairly quiet star. It's got some activity, but not, not zero, but not so much that it's kind of concerning for us. I mean, there's times it might be concerning, but not on a day-to-day basis.
And what determines whether a star is... I mean, the sun goes through cycles, and sometimes it's more, sometimes it's less. But I'm not asking so much about that as what determines a star's overall level of activity. Is it just simply like how hot it is, or is it like...
Well, there's some links. There's links with temperature. So we know, for example, that star spots can only be on the cooler end of the spectrum, if you like, of temperatures, because the very, very hot stars just don't have the atmosphere that's right to make a star spot.
Okay.
Basically.
All right. So there are certain characteristics which are related to temperature.
So there is a link there. But actually things like magnetic field strength of a star seems to vary quite a lot. And there are classes of stars that can have really, really strong magnetic fields. We don't really know why.
Okay.
Why have you got a really strong magnetic field, you star over there, and your friend over there that otherwise looks very, very similar doesn't.
And so what we don't have a good grip on what's actually going on there. We just know that they do. But why would magnetic field mean that a star is more active? What does that do?
It's all about the electrons.
Right.
So we've got this very fundamental link between charged particles and magnetic fields. It's like electromagnetism, basic 101. If you have a strong electric field or magnetic field, then you can get spiraling charged particles, the way that charge and magnetic fields interact. And so if you think about what the sun is, and this is very important why I started with the word plasma, a plasma is a dissociation of the atom. So you've got electrons that are free to move and the nuclei of the rest of the atom just sort of swimming around.
A neutral atom is positive charges in the nucleus in the center, or along with the neutrons as well, and then you've got electrons around the outside, which is negatively charged, and you put those together and you can have a neutral atom. It's just doing its thing. But a plasma is where you rip the electrons off, and you've got the positive bit and the negative bit acting basically independently.
Yeah, so if you took like the overall star, it's neutral because it's got an overall same number of negative and positively charged particles, more or less, right? Sure. But if you go into the plasma and you swim around, then you've got like some little bits of negativity over there where all the electrons are sort of grouped a little bit, and then you've got the few little nuclei over here, and so you get a bit of positivity over here, and that subtle sort of change interacting with there in the magnetic field of the star gives all sorts of interesting electromagnetic effects.
Right. And so in a similar way to, like, the Earth has a magnetic field, right? And we know that charged stuff coming from space, coming from the sun, interacts with our magnetic field and gives us things like auroras, right? At the sun, you've got an enormous amount of charged stuff, the sun itself. So if you've got crazy magnetic fields, then that gives us the potential for what we call activity, which is stuff just ripping off the thing, big, jets or loops of plasma boiling off into space. It's quite wild stuff.
Yeah, and you've got the wonderful added addition of mechanical motion because the star is rotating. You can think about the plasma moving like a fluid. So you've got charged particles moving because the fact that the sun is rotating as well, and it's rotating at different speeds at the pole and the equator. So there's all sorts of exciting physics that goes on.
You put all of this together and you get crazy activity, which can either be fairly sort of simple and not troubling, or it can be at the other end of the spectrum, which is terrifying. And our sun is sort of somewhere in the middle. It's got a bit of activity, not too bad.
Probably on the lowish end of the spectrum, but probably the distributions depend on whether you're talking about the modes or the means, perhaps. But we don't need to go down too much.
Let's not get bogged down in the stats. But bringing it back to what we're talking about, why do we care about activity when we're talking about life?
Well, you want some, as I say, partially because of some of the things that we talked about before, actually, this photochemistry. So some of that comes from the UV photons that are coming from the star. So you need some amount of release of these UV photons, and actually the particles can help as well because those particles break apart molecules in the atmospheres of planets, gives that energy source, and then the chemistry source for the biochemical reactions that can follow on from that.
Okay.
But you also don't want to go too far on the other edge because you don't want to radiate your planet and just completely sterilize any possibility of life.
Yeah, as far as we know, I mean, even with all the crazy kinds of life that we do find on Earth and how good life has been at populating all possible niches on this planet, it can still be pretty fragile.
Yeah.
You don't want to just sort of nuke it from space before it's had a chance of kicking off.
No. So you've got to be you're sort of in the middle somewhere, perhaps.
Sure.
Not too much, not too little in terms of your magnetic fields.
Okay.
And then I've actually put down magnetic fields again as another feature because the activity and the magnetic fields are linked, but they are somewhat independent. We know that there are phases of stars' lives where they go through that they're more active than other times. So very young stars are often quite violent, just post their formation. So, we're kind of ruling them out anyway.
Children, really? Yeah.
Yeah, not dissimilar. So we are ruling those really young ones out anyway because we're saying, well, life needs time.
Yes.
So let's not look
not
at
enough time, too
young.
violent, not going to look at you.
But there are types of stars that do seem to stay quite active for a large part of their lives. And this is often actually in the very low mass stars, which is sort of, again, a little bit counterintuitive. You'd think high mass stars, big, bright,
lots of energy, crazy.
Right.
Yeah.
Actually, the low mass stars can be quite violent, and it seems to be linked to.
Is that a little star thing? Are they sort of, is it a bit performative?
It's a syndrome. Yeah, I think so. But it's to do with the depth of their atmospheres and how much that can influence, therefore, the rest of the activity on the star.
Okay.
They've got these big convective atmospheres, which can then drive a lot of charged particle motion and things like that. So they can be quite active. And it's often, we're going to come back to perhaps some specific examples later in the series, but often when we look at stars around, planets around these really small stars, which include things like the TRAPPIST system and things like that, some of the most famous planets that we know of.
Right, which is a system where we found, a whole bunch of exoplanets?
Yeah, they've got
We've talked about that
7, 8 of
before.
them, So some of these systems, we find a lot of planets around these little stars, but the problem is if they're really active, are they really great planets? So, as I say, we'll come back to some specific examples, but it's just something to bear in mind when we're thinking about the broader, what are we looking for? Light, but we need to know more about what is producing that light.
Sure, that makes sense.
Planets.
That makes sense.
My number 3 further criteria, if you like, is metallicity.
Right.
This is really interesting because this is one of the things that really does distinguish different stars. So if you went and had a star that was born right now, it would have a very different metallicity to a star that was born, say, at the same time as the sun.
Right.
So long as it's in the same place and same mass, blah, 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 whatever.
Okay. Now,
same initial conditions.
We're going to come back to that because you're going to explain that. But
Yes.
first of all, we need to remind ourselves, because when you say metallicity, I start thinking like aluminium.
Yeah.
But no, you're thinking anything that isn't hydrogen and helium, aren't you?
I am.
Yes, that's that
Yeah.
astronomer
It's my
thing.
favourite thing
Yep.
to tell chemists.
Yes.
That metals are everything.
Hydrogen, helium, metal, everything else. So when you say metallicity,
Yeah.
you're talking about composition of the star. Mm-hmm. How much of that is not just hydrogen and helium?
Exactly.
And if I remember correctly, like the earliest stars, right back when stars were just like invented, it was all hydrogen and helium because there was nothing else yet. Everything else comes from the reactions inside stars.
Yeah.
Yeah.
So the universe, Big Bang, blah, 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 lots of hydrogen, right?
Yep.
A little bit of helium, maybe a tiny bit of lithium, but that's irrelevant really in the whole grand scheme of things, which is why basically hydrogen's important, helium's important, everything else we'll call a metal.
Sure.
Because everything else came after that. So the first generations of stars started fusing that hydrogen to helium, but they did other fusion processes too. And they produced some of the heavier elements, moving up to carbon, nitrogen, oxygen, magnesium. And the more and more generations of stars that you have that are born, because each generation not only just makes these elements, it sort of spits them back out into space, into the galaxy.
Yeah, at during its lifetime and particularly at the end of life,
Yeah.
when they often explode and just send all this stuff out, that then becomes the stuff of a new generation of stars, right?
Yeah, so we call it chemical enrichment of the galaxy. So there's more metals gone out from that generation of stars into the galaxy. So the next generation of stars isn't just hydrogen and helium. It's got a bit of carbon from that star, a bit of oxygen from that star, a bit of
So
magnesium.
it's starting from a more, in astronomical terms, metallic base.
Yes,
Right.
exactly.
And that accumulates over time. Okay.
And every generation produces more and more of these metals. It's a one-way direction, basically. So when those stars then go on and die, the next generation is formed at more and more metals. So presuming that at least you've got the asterisks of you're in a place in the galaxy where there's a lot of this stuff going on.
Sure,
So like
sure.
the spiral arms of galaxies, which is where most stars will form. Then the star is forming out of these previous generations, and every generation has a higher metallicity, more metals in it.
Sure. I can see that. Why is that important?
Turns out you need things like carbon and silicon to
Right.
build planets out of.
And then consequently to build life out of.
Well, indeed, and oxygen to make water.
Yeah.
and
If you haven't got all of that stuff, then all you've got is stars burning hydrogen and helium
Yep.
and hydrogen and helium. That's all you've got. Yeah, no, that makes sense.
So if you want a planet and if you want a life form that's got something that's not hydrogen.
Need metals.
You
This
need
is a
some
new
metals,
advertising campaign from astronomers. Yes.
Yes. So, and yeah, it's complex. I mean, it's not just, at its base level it is, you need some rocks to make a planet.
Rocks would help.
Rocks would be a good start. But you also need the things to make atmospheres to then go through.
all of this stuff.
I keep
and
using
helium
this
isn't gonna
fancy
do it.
word biochemistry, mostly because I don't understand the details of it, and it's easy to gloss over and say stuff happens and then
Yes.
life, right?
Yes. Get the biochemistry umbrella out. Yeah.
But yeah, so you need all that stuff basically. So this is an interesting thing because not all stars, say, born today. If you took all the stars in a galaxy and all the ones that are going to give birth to 10 different stars today in the galaxy. Not all of them are going to be born with exactly the same metallicity, even though they're all born at the same time, because it depends on what their local environment is. If they're born in a spiral arm that's happened to have had lots of generations of stars go around their life cycles, you're going to have lots of metals. Wonderful.
Yeah, great.
Right. If you're in the halo of the galaxy, the outer reaches way far away from the spiral arm, it's kind of just cruising out there on your own, and you happen to accumulate enough mass to collapse and form a star, you're probably going to have a much lower metallicity.
Sure.
Because there's just not been the same number of generations go through.
Yeah.
So it's all very local and environment dependent as to individual stars, what their metallicity is, but it affects their fusion. And therefore it affects things like their temperature, their mass, their lifetimes, and what their energy output
Right.
is.
So do we see different characteristics in stars which are different metallicities? Like that's definitely a characteristic.
Absolutely.
Well, you're behaving like this, and that's partly at least explained by the fact that you got all this other stuff in you.
Absolutely.
Okay.
Yep. And particularly when we look at doing really long-term models of how, because we don't witness stellar evolution happen live in front of us. We don't have the fast forward button on the remote, but we can use models to kind of bridge the gaps in between star A, star B, star C, and say, well, you must evolve into you and you must evolve into you. And so with those models, you can see very clear differences. If you up the metallicity, it will change how that star
Right. So
moves through its life.
metallicity, all the other stuff, all the other elements, gives us both changes in characteristics of your star and the stuff that you can make rocks from.
Yeah.
And all the things that might live under those rocks, for
Indeed.
example.
Yeah.
Okay. All right. That makes sense.
So you need to have, therefore, stars that have some metallicity, and we'll come back. I don't think there's maybe a maximum, but they need to have some. Sure. Maybe more is better because then you get bigger planets. I don't know.
Here's a question. Of all the planets that we've found, all the exoplanets, like you were talking before about like if a star's forming out in the halo somewhere and it doesn't, like it's not in a high, a very rich metal environment. And so a new generation of stars might form that are not terribly more metallic than the ones that came before. But presumably out of, a swirling bit of gas, dust stuff, you might get a star and still, a disk around it. You could form planets. Do we find exoplanets which are just not very planety? Like, do we find planets which are basically just small failed stars that aren't chunky and rocky and metallic?
Yes, absolutely. So these are often our gas giants, of course.
Right.
If you think about even the composition of our local Jupiter and Saturn.
Yeah, what's Saturn made of?
But quite a lot of hydrogen.
Yeah, okay.
Yeah. So if you've got a lot of that sort of primordial-like gas floating around in your system, you might not be able to create a really big rocky planet, but you might be able to create a core that then sweeps up a lot of the leftover hydrogen and so on, and that's kicking around.
Right. Yeah, that makes sense.
And even Jupiter's got a very metallic hydrogen core. So even the core, which is somewhat solid hydrogen.
Right. Yeah.
So it's not even like you've got kind of rocky Andes sitting underneath the atmosphere of Jupiter. It's all quite hydrogen.
It's a lot of metallic stuff mixed in with a heck of a lot of hydrogen.
Indeed. So metallicity is important.
Okay, so that's number 3.
Yep. And number 4, this is quite a fun one. Not all stars are alone.
As in, you're talking like multi-star systems, binary systems, tertiary systems.
Trinary, yep.
Trinary, yeah.
Quadruples, quintuples. I think the maximum is like 7 or 8 that we found.
Really?
In one system.
I think we talked about that, but that sounds quite surprising and not, that can't last. That's not a relationship that's going to last.
So I mean, the commonly bandied around statistic, which is more or less true, is that about half of stars are born in pairs or higher level systems.
Okay. So we know that. How does that impinge on our question of the potential for forming life?
Well, multiple systems can be very disruptive to planetary systems, depending on their organisation.
We know it can happen because Star Wars.
Yes,
right?
well,
Tatooine.
that
Luke,
documentary
Luke
about
was there.
that life on that other planet.
Yeah. So we know it can happen, but
Well, yeah, but even the scientific foundation for that is fairly solid. I mean, Tatooine-like planets have been discovered around binary systems, and those systems are where you've got a binary star system where the two stars are quite close, and then the planet orbits at some bigger distance further away.
Right. So it's not a planet going around a star and then that going around another, or co-orbiting with another star. It's the two stars in there, like you often see in the pictures from the Star Wars of the two suns.
Yeah, going down
setting.
the side.
They always seem to be right on the horizon.
Yeah. Well, that's when the light is best for filming, I think.
Yeah, I think so. It's constantly golden hour in Tatooine. Yeah.
But you also get systems of the first type you described, where the planet's going around one star, and then that planet and star as a pair are going around a second star. So
I can imagine in either of those cases that could be pretty disruptive.
There seems to be very limited options when it comes to orbits of planets that will remain stable in these kinds of systems, because if you imagine the video of the two stars and the planet, if you push play again and fast forward, there's so many ways that can be disrupted due to the particular alignments of the gravitational forces that it doesn't seem like many orbits are basically stable for long periods of time.
Yeah, you might get stability for a little while, but it may not last. And again, kind of coming back to the whole, what's the chances of life? Like, you want things to be a bit stable. Just to give it a chance.
You're also going to have changing amounts of light, right? Because sometimes you've got two stars, one there. Sometimes it's together. Sometimes changing temperatures, but things like that. So it's all quite speculative. So I wrote down literally, it's not a no, but
let's not look there first. Let's not put all of our eggs in the binary system basket, let alone the 7 stars.
I guess the one thing that does help us here is that if we have already decided that those big hot OB stars are not good news because they don't live long enough, they've got too much energy. Let's not even talk about what they're going to do when they die, because that's just not useful for anyone who wants to live on a planet there.
Mind you, I don't want to be here when our star dies.
Well,
so
no.
It doesn't have to be big and crazy.
No.
Just don't be anywhere near a supernova. I think
Exactly.
we've discussed before. Just don't.
No.
If you have a choice, don't.
It's not a good idea. But the good news, I guess, in this context is that actually those very big hot stars tend to be much more likely to form binaries than smaller stars.
Okay.
So it's just the orbital or the gas dynamics of once you've started your collapse of your cloud. If you've got a very big cloud, it will tend to collapse into two big stars. And if you've got smaller clouds and they sort of more rarefied into clumps, you tend to get more single stars being formed.
I can see that. See that.
So if we're saying, which I think we are already alluding to this, that the lower end of that temperature spectrum is probably a better place to be starting out looking for life around stars, then the good news is that fewer of those are binary and higher order systems.
Okay, because that's good. Because if you'd sort of, like, I've had the sense so far in the things that you've discussed that it's like, well, the hot ones, like, they're cool and everything. Well, they're not cool. The hot ones, they burn out quickly. Like, they don't give you a lot of time. No. They're exciting, they look good, but they don't last very long. So, well, okay, maybe let's not look there. If you had said, but the trouble is the cool ones, they tend to form lots of binary systems. So, okay, let's not look there. Let's just not look anywhere. There's no life anywhere but it does sound like, after going through those 4, that we do have some parameter space that we can start considering for, all right, if we need to look at stars, which we do, we're not just throwing them all out saying you're all too hard. It could never possibly work. We do actually have a sizable chunk.
Yeah, but it might be a smaller chunk than perhaps we've let on, really.
Okay.
Because remember, we've rolled out those hot, big blue stars. It's not great going down to the cool, low mass dim stars, because they're the active ones that are kind of blasting
they're a bit violent.
their planets and so on. So we sort of are heading towards the middle. We don't want them to be too metal rich. We don't want them to be too metal poor. Mm-hmm. We don't want them to have too strong a magnetic fields. And actually that starts to draw down stars that are even just a little bit of hotter than the sun, because they tend to have stronger magnetic fields. We don't want too much activity, which the very low mass stars tend to have quite a lot of spots and so on. So that's probably not great either. So it does feel like...
So we're sort of whittling it down.
Yeah. The walls are coming in a little bit.
So can you...
at this point.
Are you able to sort of characterize where we've sort of found ourselves then in this discussion, as if we were going to go and hunt on the basis of star type, where are we looking?
Well, I think we need to start with stars that look like the sun.
I mean, I don't know. That makes sense. Like, it's the one that we know. And if you look at it the other way around, maybe that's why we're here. But it's pretty funny.
It is a bit. It's a bit.
Who'd have thought?
I know. You do all this work, all this science, and you could have just said, "Hey, let's just try and look
for ones like us."
Yeah. It's interesting. The thing is, we've got to also now rewind a little bit and think about not just suns. So if we want to think about much more broadly, let's say we're going to now survey the galaxy. We're going to find all the stars in our galaxy that look like the sun.
Mm-hmm.
Now, the bad news is that suns they're not super rare, but they're not super common either. If you were to take a sort of some census, then about 8%, depending on how you do the statistics, of stars in our galaxy are similar to the sun.
Okay. And I mean, is that simply because there's lots of different kinds of stars, or is it that there's many, many, many more stars which are, for example, the big bright blue ones?
It's the other way. There's very few stars that are the big bright blue ones, and there's, partially because they're all gone through their lives and blown up, sense. Right? Yeah. Whatever. But also they just tend to form. Many, many fewer of those really big stars are formed in a given period of time in the galaxy. So actually the most common type of star are these really low mass, really red, small, dim stars.
Right.
And we're sort of on the middling sort of area of that distribution. Okay,
so at least it's not, 0.8%. At least it's 8%.
Mm-hmm.
At least that's some. Rounded up to the nearest 10%. It's like, 10% of all the stars. And there are a lot of stars, so that gives us a lot of suns.
Yeah, but now we need to throw out a whole lot more.
Right. Which ones are we getting rid of now?
We're going to throw out all the ones that are not in the right place in the galaxy.
Okay. And what's the right place in the galaxy?
So
there's good, bad. There's good
and bad places to be in the galaxy. Right. So this is actually coming back to that metallicity argument somewhat as well. So let's even rewind a little bit. Let's talk about habitable zones. Most people would have heard at some point, if they're interested in exoplanets and looking into them, that there's a concept called the Goldilocks zone or a habitable zone. And this is the area of possible orbits around a star where temperatures are not too hot, not too cold. They're just right.
Yeah.
So Goldilocks zone. Mm-hmm. We try and be a little bit more scientific by calling it habitable zone.
But look, let's face it. It's a catchy phrase that works well in the media. So let's go with Goldilocks.
So I haven't really mentioned that because that's more about the planets, right? And where we find the planets.
Yep.
But it turns out there's a similar concept for stars in the galaxy. And there is what we know called a galactic habitable zone.
Okay.
Or a galactic Goldilocks zone.
Mm-hmm. So, I mean, the Goldilocks zone for planets is talking quite specifically about, it's reference to life, right? It's not too hot, not too cold for life. Mm-hmm. How does that apply to stars and their position in the galaxy? Or why?
Well, this is still true for life, but it's just saying you don't want to be too close to the center of the galaxy. You don't want to be too close to the outer edges of the galaxy.
Because, the outer edges, you haven't got enough stuff. That's the whole
there's no metals,
thing.
Yeah.
And the center? Because there's too much going on?
There's too many stars. It's a bit too dense. Yeah. You're going to get orbital disruptions from all the other stars kicking around close to the center.
It's like a big city. You don't want to be right out on the edges where it's like there's nothing going on. But you don't want to live right in the center either because you'll never get to sleep.
Yeah. There's too many supernova going off. You might have an active galactic nuclei that kicks off from time to time that completely sterilizes all the inner galaxy.
Yeah, that's not good. You don't
No,
want that.
gamma ray bursts. Like all these nasty things happen in the centers of galaxies. They're just there. So you don't want to be there. But equally, you don't want to go too far out because you won't have the metals that you need. So there's a sweet spot.
Right.
And there's a sweet spot in terms of distance from the center, and there's a sweet spot in spiral galaxies in that you want to be in the disk and where all the spiral arms are.
Right, as opposed to above or below the disk if you're looking at it kind of side on,
Yeah.
in the sort of, what do you call it, the halo.
Halo, yeah.
Right, you don't want to be out there.
No.
You want to be in the disk.
There's no transportation networks up
Yes,
there,
that's
basically.
right. You want to be on the transportation hub,
Yep.
but you don't want to be right in the center.
No.
Because that's just too much.
Yeah.
Yeah, okay.
So that's the concept of a galactic habitable zone.
Sure.
So even if you took your 8 to 10% of stars that are kind of similarish to the sun, you've got to now throw out, I don't know, 2/3 of them, something like that, because they're not in the right place in
So
the
we're
galaxy.
down to a couple of percent of all the stars are the ones where, at least by these criteria, we're looking at and going, all right, let's have a good look at them.
Yep. And then throw out a couple of percent because you've got multiples in there. You don't want the binaries and whatever. Throw out a couple more maybe because of the magnetic fields aren't great. They're a bit too strong. The star's got a bit of a chemical peculiarity or something weird else that's going on.
Are you
with
about
it.
to tell me that we're basically whittled this down to, in our galaxy, there's one and we're it? Is that where we're going here?
I'm afraid that is possibly the most likely scenario.
At this point, I'm going to start believing in a benevolent God. I think, like, this, come on, this is getting silly.
The statistics don't lie, though, do they?
Yeah, no, but in all
Unfortunately.
seriousness,
Yeah.
like, where do we end up in this conversation?
We do. Okay, well, if you take the 6,000 or so planets that we have detected around stars, we're sitting at around about 200 that are around these stars that are similar to the sun, and then maybe half that for ones that are just not in the right place with multiples, blah, 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 whatever.
Right, okay.
So maybe about
that's-
100.
And that's before we've even looked at the characteristics of the planets
Oh, yeah,
themselves.
yeah.
This
It's
is
nothing
just,
to do with the planet.
of all the planets, which stars make them just even possible that we could look there and say, is this worth our time?
Yeah.
And we're down to, out of 6,000, a couple of hundred.
Maybe 100, yeah.
Maybe 100. It's better than none.
It's better than none.
It's definitely better than none. It's frustratingly low, but it's better than none.
But then, well, there's always a little bit more.
Yeah.
Well, and I don't know if this is good or bad, actually, at this point. I suspect it's a bit of both. Turns out we're actually not very good at measuring stars. So if you're saying that we need to kind of narrow down our like top hit list of really good stars to look for planets around, we're actually only good at measuring massive stars to, well, in the very best cases, maybe 5%, but usually more uncertainty
worse
than
than
that.
that.
Worse than that. Radius, again, 5% if you're lucky. Usually it's much worse than that. Temperature, 10% if you're really lucky.
Really?
Of
Wow.
your uncertainty and temperature. Yeah.
And I'm imagining those kinds of uncertainties have a pretty big impact then on, well, we think this star might be good, but actually it's probably not.
Well, yeah. And age is even worse. That's the worst one of them all. You're looking at 20% or more of an uncertainty on your age a lot of the time.
Wow. So how does that impact then our ability to identify potential candidate stars to look at, to go, is like, can we see anything here?
Well, yeah. I mean, you can still pull all those stars together.
Yeah.
The problem is when it comes down the line to say what we're going to talk about in the future episodes of, okay, is the planet in itself, is the environment suitable? It might mean that you've got uncertainties of 30, 40% in some cases on the temperature of your planet. And that's just not easy to work with.
No.
I mean, if you say something's 100 degrees plus or minus 30 degrees,
That makes a big difference.
it does make a big
Does make
difference.
it- I
or
mean-
even 0 degrees plus or minus 30
You
degrees.
think about how much we're thinking really, really hard right now about a difference of maybe a couple of degrees on our planet, and how much that's going to make a difference. Yeah, 30 degrees.
But that's
30%,
actually, no, that's a smaller error. But yeah, so
Yeah.
if we talk about Kelvin, then
Yeah.
you're actually talking, closer to 100 degrees.
Yeah.
0, there we go. There's a better analogy.
Yeah.
0 degrees plus or minus 100 degrees. That's a big
That's
range.
brutal. Yeah. That's the difference between just, the coldest place on the planet and then some, and, an oven. It's just, yeah, okay. So, Emily, what I'm reading is that we basically have very, very small chance of narrowing down all of the stars that we see to a reasonable number that we can explore to go and look for potential signs of life on the planets that may or may not be around them. But we're doing it anyway.
And I have 2 rays of hope to give to you in this process.
I like to end an episode with not just 1, but 2 rays of hope.
Shining light rays of hope.
Hit me with it.
From solar from stars. So the first one is we're getting better at measuring stars.
Good.
And we've got some wonderful techniques, astroseismology, which are getting these errors down to...
Emily's throwing in a plug for her own field there.
Yeah, I am. They're getting some of these errors on things like temperatures and ages, even down to percent level. Doing much better.
Yeah.
That's very good.
That's a hell of a lot better than...
And if you want to know more about that and how it works, then refer to episode X that I can't remember the number of right now.
Yeah, go back and do a search through our back catalogue for astroseismology.
Yeah, and find out some more about that, because that's very cool and very exciting. So we are getting better, and we'll be able to therefore know more about stars, and then we'll know more about the planets that are going around the stars.
Thanks to the work of people like Emily.
Indeed. I can't really claim that much credit for it.
No, but I said people like you.
Yeah, exactly. And the other thing is that we don't have to necessarily restrict ourselves to this idea that we are looking for an Earth-like planet around a sun-like star, because we have wonderful examples of the adaptability of life on Earth, and there are lots of other environments that are in our solar system that we still believe might potentially host life, whether it has evolved there itself or whether it's gone there, moved there. And therefore, when we do look at other exoplanet systems, there's lots of scenarios of exoplanets that might be life hosting that are just different to our Sun-Earth system.
So after having whittled everything down to, we're basically looking for things like us, our kind of star.
I mean, that would be nice.
Habitable zones that make sense to us. We've got to be open-minded for the rest of this conversation over the next several episodes about where to look, how to look, what are we looking for? We can't just look for, creatures that are about 6 foot with 2 arms and 2 legs and, nice hair. That's not what we're looking for. We're looking for something else in places probably unlike anything that we know.
Yeah. Now, that's not to say we're going to go way out into the science fiction realms here. No. We are going to try and keep ourselves relatively constrained to life as we know it, but survivable in environments that are different, if that makes sense.
Sure.
So I think that's something to really, I guess, as you say, look forward to and something to explore, and a really nice lead into the next episode where we're going to start to take, okay, we've got a star, it's an okay-ish star, and let's look at some of the environments that we might find life around those stars.
Excellent. Episode 2 coming your way soon. Well, Emily, I was getting worried there for a minute because I really, really thought that you were about to tell me that call off the search because it's just us, right? There's one star in the galaxy which is suited to life, and it's us, and we can all just pack it up and go home because there's no point. And you haven't said that. We do still have 5 episodes to go in this season of Syzygy. We've got to fill it with something. We can't just fill it with, so have you seen life on Earth? Look how cool we are. We need somewhere to go, and I'm glad we have. So thank you.
Yes.
I appreciate that.
Well, and I hope that everyone listening comes up with a newfound appreciation for our stars and how important they are, even when we're looking for other planets.
Yeah. And
so I think stars are undervalued.
I think they are. And I can't help but sort of think about how, we are rather life-centric, as a species, because it's us. And, we're on a planet which is teeming with life. And it can be just, very tempting to think of the universe from the point of view of how much life is there out there. And that's what we're obviously doing in this season. But this discussion just brings home how much stuff there is out there which is not life and it's all really cool, but it's not life.
Yeah.
And it's not for life. It's just there.
And if nothing
awesome.
else, I'm sure I'm going to end this series as I end most of the times I sit and think about life in the universe, just thinking, wow, there's a lot of things to think about. There's just a lot of input. So it's overwhelming if you let it be. But it's important just to appreciate that there is a lot.
Well, listeners, if you're sitting there thinking that is a lot and you want to share some of that thought with us, there are various ways that you can do that. You can still get in touch with us. Probably the easiest way, Emily, is through our website. You want to remind us what that is?
It's syzygy.fm, syzygy.fm. We've got the extensive back catalogue that you can find on there, and you can find those astroseismic episodes. There's probably about 6 of them, to be fair.
Because Emily does keep coming back to it. I don't know why. It's weird.
I keep banging on about it.
Yeah.
But you can also find some other cool things. You can obviously find the show notes and things for this episode. You can find the little contact us button. And you can also find a wonderful Great Wall of Thanks.
That's right. And the Great Wall of Thanks is for all of the people who have supported us over the years that we've been doing this podcast. People who have supported us both, in kind, like people here at the University of York, where Emily is based and we are currently sitting, all the way through to the people who support us on Patreon. There are a bunch of you out there who have seen us through the good times and the hard and help us to keep the electrons flowing through the podcast and the website. So thank you to those of you who support and continue to support the show. And if you want to see who those people are, go to the website and go to the Great Wall of Thanks. Listen, if you want to help us, you can do that by contributing cold hard cash through our Patreon page, patreon.com/syzygypod, or you can just share it around. Tell people that you know that there's this fabulous podcast called Syzygy and they should listen to it because we talk about awesome stuff, like whether or not there is in fact life in the universe. Emily, we'll be back soon with episode 2 in season 3, Life Amongst the Stars. See you really soon.
Catch you later.
It's going to be good. Bye, everybody.